This session kind of follows the previous one. It's about inferencing, but not on the KV cache side, but more on RAG. And this is more like a summary of what I have to understand in order to get value out of DISKANN, because it was interesting. Like a couple months ago, somebody showed me a report showing numbers that I couldn't understand, and I wanted to compare or have an idea how to compare. So a lot of echo. So, okay. So anyways, this one. So what are we going to see today is more how I kind of built that understanding of vector databases and how it just made sense to me. All right, okay. So I'll be starting with embedding vectors, search, and I think we may get better now. Yeah, that's way better. Way better now. Thank you. So restarting. So the way I build that knowledge is, okay, understanding what's our embeddings, vectors, or the vector database, similarity search, and indexing. And the most important, how to compare different indexings and to get to the point where the point of the talk actually is DISKANN, which is another offload, storage offload technique for indexing, which we've seen with KV cache. Everything kind of happens in memory, or in this case for RAG, DRAM, main memory. But the memory wall is getting to the point. The data is growing too much, and we don't have enough space for all the data that we are creating. So starting with vector database, why do we use them? There's so many applications, but they provide similarity search. So the thing that we want to understand is vector database provide similarity search. And this is what gives RAG the response. So it is not an exact response, so it's not 100% right, but what are the most likely correct responses? So there's one big difference in the search for using vector databases that mostly there won't be an exact answer, but what is the most likely correct answer? So that will be very important to remember. So talking about vectors, sometimes we understand vectors as from our physical science, right? X, Y, Z, how to do arithmetics, and they're normally spatial 2D, 3D, but with vector database in data science, they are very abstract, and not millions, but could be thousands of vectors and points. So that's one big difference is, we are dealing with spatial X, Y, Z, so we have to forget about that and work about, how many dimensions, thousands of vectors. And we are trying to locate proximity. So we use cosine L2 to understand in the vector database what are the clusters or pages that are closer together. And that's what's going to be give you meaning. So when we talk about similarity search, some concepts like embedding, similarity, KNN, clustering, indexing, recall, those are very important. So embeddings are the representation of the vector. Similarity is how close things are one to another. KNN is the number of nodes, clusters that are closer. So that's kind of the response that we're going to get, right? Clustering are the partitions. So a vector database can grow so much, so we need to divide shards. So those are clusters. Indexing is what enables the search. So another interesting point is if you know regular database management, RDMS, like Microsoft SQL, Oracle, you don't necessarily need to have an index to query the data. It's just that's going to be slower. On a vector database, you need the index. So if you don't have the index, you don't have access to the data. So it's not only for speed, but actually to access the data. You access the data always through the indexing. And recall is the measure of quality. So it's one of the key important factors when you're comparing two techniques and two answers. You need to know the recall, right? So how good is your model? And that's going to be one of the points that you need to compare. You need to know what's the recall rate when you're comparing A, B, and C indexing techniques or models. Because if you don't know, that is just, it is meaningless, any type of measurement like queries per second and latency. So embed this just a little bit more is high dimensional, dense, you enable similarity search. And one thing that I kind of understand, the similarity search gives the idea of the intuition because I can put things together and understand that one thing is related to another in the vector space. This is kind of an example what a vector, an memory is like. It's just you putting a lot of qualities in the object. An easy, simple example, actually not easy, but a simple example of vector similarity search is doing arithmetics. So in this case, I can infer, or the system can infer if a king and man, queen and woman. So if I have a king minus a man, I could have something like that. So you have the coordinates of every object, and you can do arithmetics with that and come to an answer. Right. So that's one of the techniques that we call the similarity search. We always do vector math. So in order to kind of understand DISKAN, which is one type of indexing techniques, we kind of go over other indexing techniques. We're just going a little bit, just sitting, just touching on each one, just to have an idea when we talk about DISKAN. One is flat, or brute force is just basically an array. There is no coordination. Actually, if you create an array, you create a flat indexing. It's compute intensive, and normally is used for very small data sets, right? Because you don't have any techniques to search. It's actually a brute force search. You go to each entry till you find the answer that you're looking for. And this is the only technique that gives you 100% of certainty, because since you're going to every single entry, you're going to have an exact match. Our other techniques are not exact match. They are close enough match. Another very popular one is a tree-based, which is you can call annoy as well, but it's another similarity search. It's a binary search, so you kind of divide your vector space in clusters till you get as sparse enough or you have enough neighbors and connections. Again, you can go and go and go and go till you find that, but then the more you break down, the more clusters you create, the more connections you have. So it will take longer to fetch an answer because you have more connections. So everything in inference RAG, it is about the trade-offs, right? How exact you want to be or how fast you want to be. Those are going to be one of your parameters. Another one is how many queries you want to do in a particular data set. So ANN, approximate nearest neighbors. Basically, I pick a point and retrieve as many neighbors as it is set on your search parameter, right? So I can retrieve 10 neighbors, 20 neighbors, 100 neighbors. That setting also will determine how fast you're going to have and how exact your answer is going to be. Another very common indexing technique is a graph-based. So if you hear HNSW is a graph-based technique. So they use, instead of clusters, they use small worlds, which is basically, we start with a top layer point. It's a random point in the vector space, and we start creating small worlds connected. So again, I create a map of connections. Everything in vector index is going to be a map of connections. It just matters how you build that, those connections. Those are going to be your. Another common one is IVF, inverted vector files. Again, you create points, clusters, and you may have heard about KNN, which is basically give me a certain number of nearest neighbors. And this number, K, it is what you make up. So it can be 100, like I said, it can be 25. It is a number that you're comfortable about creating those partitions, right, or clusters. And then there are the quantization-based, which they were created more to preserve memory, so they are less memory-bound, so they require less memory. So you have two main types, scalar and product. But basically, I'm using less precision. So you create a smaller indexing. So by using less precision, you already know your recall rate may suffer because you're taking away precision to have more speed or to have less memory pressures. Those are the two types of quantization. And then we have hybrid, where DISKANN is going to be, which is I choose more than one technique. And those come again on the requirements, how much memory you want to spend, what's your precision point, what's your recall. So the quality of your search will be met, right? So you have the requirements. So again, it's not one is better than another one. It's just what are the trade-offs that you want to have. Right. So DISKANN is considered a hybrid because it's going to use graph and is going to use compression. So when we get to comparing vector databases, or vector indexes in this case, so we are doing a search, so we're using that index, we need to know the recall, right? So we create buckets of recall. like 80%, 90%, 95%. So think about on the storage world, the percentiles, right? So we have the 95 percentiles, the 90 percentiles. So where you want your recall to be, and then you compare latency and throughput. So if you don't have that, if you're comparing a 50% recall rate to a 85% recall rate, you're going to have really high query per second on the lower recall, because you don't care much about the quality of the answer, but how fast you want the answers to be. So the lower the recall, you're going to have better numbers, but the quality of the answer is going to suffer. Again, that comes with your trade-offs, right? So you need to know the trade-offs to choose one, and you need to know where are you at the recall requirement in order to compare 2, 3 indexes to choose which one is better for you. I say that because now when we talk about DISKANN, which is using storage, using block storage to offload part of the indexing, you will see some numbers that are counterintuitive with what we expect, right? We expect our in-memory indexing to be faster than an offload in disk, but it might be the case for certain types of models, certain types of search, because we get what's your recall rate, what's your type of indexing, how many neighbors in that indexing are you creating, right? So when we talk about KN, clustering, and graph, we have the density of the index, which will be how many points are connected to each other. So the highest that degree, that density, the slowest is going to be your response, because I have to query and retrieve more information per query because I have more neighbors, right? So it's just on the street, if you have 3 houses, each house has 2 neighbors, but if you have 100 houses, the number of neighbors per house will increase, and so it will take longer. And also, the index creation, which is the build time, will also be affected. So for HNSW, and by the way, all the previous ones that I mentioned, they are all memory-based. So once I create the index, they all live in memory, right? But this KN, which we'll see there is some memory part and disk part. But you can see here, for instance, for HNSW, you have your queries per second and your recall time, right? So the higher your recall, so the better quality you have, the lower query per second you have. Again, this is just how it is, and then the number of vectors. So we're talking 10 million, 100 million, and a billion vectors. Those are going to also influence on how fast you can query and how well you can query. And also, we heard in KV cache and vector database is going to be the same. What's your precision point? So you can have FP16, FP32. So FP32 carries more information. Thus, your index is going to be higher or bigger. So we require more memory, more time to build, and so on and so forth. So that choice is very important when you're comparing. Again, if you're comparing a FP8 and with FP32, also you're going to see different results for the same model, because you have different amount of information per vector. And that was something that it took me a while to understand. Yes?
Yeah, so that's assuming no rewriting, right?
Correct.
Yeah, so like you can basically achieve the same effect, but you fetch a large
Well, in this case, it's not about the token, because the tokens are when you have an input, right? So, and RAG, in a sense, is just to extend the knowledge base, right? So we don't have the idea of tokens. It's just part of the input requires a set of documents or a set of knowledge that was not part of the training. So you don't have the idea of tokens. You have idea of, okay, I'm giving back this information to the inference pipeline, and then that's going to.
Yeah, that's what I mean. Like over here, your the recall is close to 100%, and your fetching also fewer tokens that if you fetch a large number of tokens and those are DRAM that you can.
Yeah, but not in the idea of a vector database, but in the idea of the model that you're using, yes. On the idea of vector databases, you're doing a query of X amount of neighbors or points, right? And that answer is going to be based on how you built that, right? And one thing about vector databases are most are not real time, so they don't update real time. So there are new data, and they just update the index. Normally, you have to rebuild the index, and that also is like the drawback for having that, because it's very static. Once you have that pool of information that you want to extend your LLM, in this case, you create, and then if there are new information, you normally have to recreate that index. But yeah, so when you talk about tokens, it is an inference pipeline, but when it gets just for the vector database, it's just get a search for that. All right. So, but again, this is just to show the influence of many things, right? The number of vectors, the precision, right? And the index technique is going to affect where you are in your numbers. So your queries per second, your throughput, your latency. So DISKANN came to that point of the memory wall, like we saw in the previous presentation, right? So we have a finite amount of memory in a particular system, right? And from a point on, you have to expand, scale out your solution in order to accommodate all the data that you need to be indexed in this case, right? So one code is like the current state of AN search generates ints that must be kept in memory. So that's one of the limitations, right? So the higher number of vectors we have with X amount of dimensions on that vector, we need more memory, right? And that comes to a point where you need to scale out, and scale out adds more latency because I need to crawl every single shard of that index that is divided across the nodes. I need to go across every single shard. So that's going to, a point, increase your latency, right? Because you need to crawl many nodes. So across network, your east-west communication, you get that. So one study that bring to DISKANN is, okay, let's put part of this index in disk, but at the same time to minimize as much as possible going to the disk. Because we know as a storage, every time we go to fetch something from block, from disk, from storage, you pay a really big penalty. But creating different techniques to create those index, you can achieve the same quality that you would expect from HNSW, from ANNs, which are all based in memory with disk offload. And that will create a less demand for memory, which is one of the biggest things for DISKANN. So one example, I have a regular computer, 64 gigabytes of RAM. I can run 1 billion data points or vectors, right? This is S1, SIF1B is just a data set that you can find in the internet. And we can achieve, for instance, 5,000 queries per second at less than 3 milliseconds at 95% recall rate. And so those are numbers that are comparable with regular indexing. Right? And again, when you're doing the comparison, you want to know everything there, right? Your data set, your amount of vectors, your dimensions, right? That's what you need to know. And what's your recall target? So okay, I want 95% recall target. Right? So that's where you're comparing. So talk about the RAM footprint, right? So since we talk about every indexing technique being memory, right? Stored in memory. Here is how much what's the percentage of the data set that is physically, when you create the index, how much is going to be in RAM, in percentage. So we have different indexing techniques, and now you have the percent of data set that's actually stored in RAM. One interesting thing, obviously, RAM or raw, it's going to be 100%, obviously, if you put everything in memory. But HNSW, actually, you need more memory than the physical data, just because the way you create the indexing. This again, just to have an idea why we are doing DISKANN. So when you created the indexing, and that's going very closely to any type of index technique, right? You have the data, you create the embedded, you cluster that, you start building your graphs, right? So when you get the embedded, you compress the data and you add to DRAM. In case of DISKANN, we have two parts, the DRAM part and the SSD part. But there are different things that are stored. So when you talk about DRAM and DISKANN, we store a very compressed view of my graph 3 base. So think about HNSW, very compressed and with a lower precision. So it actually stores with a lower precision, right, in DRAM. So your DRAM footprint is very small. And on the disk part, or what we have is out the graphs that were supposed to be created as a graph-based index, it creates kind of a flat file. So there are no, a lot of layers. It's just a flat file, which makes easier to fetch data when I don't have that. So what's in memory, I have just the points and the number of neighbors, and which most of the time give you the exact location where you have to go to that flat structure to retrieve data. And that accomplishes the point of not having to go to the disk a lot of times. Because normally when you have that type of offloading and just a regular indexing technique, every time that I, let's say, have a miss, so I retrieve a number of neighbors, but it's not where the search needs to be, I have to go back and go back. And that kills your performance just because you're going to the disk so many times. So one idea of DISKANN is the information that I have in memory in DRAM is good enough to have very few trips to the disk to actually retrieve the data. As part of the architecture, it's a Vamana-based algorithm. So we have, like I mentioned, memory and disk hierarchy. So in memory, we have compressed representation of all the points. And on disk, we have that flat graph, what they call Vamana graph. Other points of the disk is we have offline reordering, and the graph connections are in sequential layout, which we kind of touch base that. And the type of search in the disk, instead of being a greedy search, it's a being type search, which is no hierarchical over a single flat layer, which basically comes back to the point, let's not do any unnecessary trips to my disk. So another way to represent that, right? So let me get a little bit closer so I can read. So that's kind of how you represent RAM. You have all the embeddings compressed, and on SSD you have the full embedding and IDs for the neighbors. So again, on that flat graph, I have the complete structure on the flat line, but I know all my connections. So when I retrieve information from a particular vector, I also retrieve all the connections that are made. So I don't need to go to the disk again to know that. So I can be very effective, and in this case, produce results that are comparable with AJ/NSW alone, or sometimes even better than AJ/NSW, depending on the model type and where you want to be, which we're going to look a little bit later. Just reiterating what I've talked about already, right? So regular search operations, they are high disk I/O, so not good for your performance, right? With this DISKANN, it's we fetch neighbors sequentially, so low disk operations. So we go and we cache data in DRAM. And interesting enough, that caching data is updated throughout the life of the indexing. So as long as it is up and I'm having searches, that map that is in DRAM is updated. So theoretically, with time, as more you use a DISKANN indexing, it should get better results just because I'm updating that. That all comes to those types of results. That's kind of a study that SolidIM did with a Metro AI, and we get those type of results, and that's why where I started to look at it, because they asked me, like, do you agree with those numbers? And I just like, I don't know. I don't have any idea of how to interpret that. Most is you telling me that our in-memory indexing is as fast as a disk offload. That does not make sense, right? Thus, it must not be true. But I start digging and how we came to this type of answers, and actually surprised me as well. Just like, yeah, it does make sense. So in this case, we have for a 100 million vector, actually 10 million vector, this one. It's there, 10 million vectors and 768 dimensions. Those are the comparison between AJ/NSW and DISKANN on both latency and QPS, right? You can say, oh, actually, HNSW is higher latency, but just looking, you see that they are very comparable. You could use DISKAN with the same search quality as HNSW with, let me go here, just skip, with the advantage of not having too much memory needs. So these are numbers from Milvo's sizing tool, where I did a 1 billion vector, 768 dimension, and how much it would cost a solution purely based on HNSW and DISKAN. And so I have there how many cores, the memory, and storage. Obviously, we have local disk, which on HNSW we don't need local disk because it's our memory. We're reading from remote storage. But the point here is if I put that in a cloud, I'm spending $9,000 against $23,000 monthly to have basically the same result, same quality of service. Yes?
Can you give us some insight on why this is the case?
Yes. One is because HNSW is not as, it does not have the efficiency on search that combination of having a compressed index with all connections have, because HNSW will not get all the connections with each point. So I have to go to that graph in order to find all the connections. The way DISKAN is created is that each point in that database, I know all the connections when I do the search. So actually, it's very efficient on going to find the neighbors. And once I know the address, I have to go to the disk and fetch the real data because I have just compressed it, low precision data in DRAM. But the result is that both basically have the same performance, right? In this case, in this model. So you have to test every single type of model, but from what I have tested with real data sets, it's very, you find these very comparable results. So that's, it's an interesting part. Yes?
On the next slide, keep going.
The cost.
So the difference in storage is kind of stark when you look at the DISKAN end. Is that because the size of the indexing method on the HNSW is a much larger storage footprint?
Yes. In this case, it is a larger footprint because we don't have we don't create that low precision part. So every point on the HNSW has the same precision. So it has, on the DISKAN, you have those two different types. But since it is memory bound, obviously, I'm doing the same work with less cores or less CPU because I need less memory, right? And that is the main point. So if I have to create a solution to support 1 billion vectors, which today is like, okay, we have benchmarks for 1 billion vectors, but it's very rare that people would be using that. But if you have to, this is what would cost you monthly on a cloud provider. Just because you would need X amount of instance to have that 4.2 terabytes worth of memory, right? Because you have that ratio of CPU to memory, right? Or vCPU to memory. And the additional part is that you would need local storage because I need that local NVMe in this case to get the flat graph. Going back, if you're tuning this KNN, those are the parameters that are available. In this case on Milvus. Why Milvus? Because it is the current vector database that supports DISKAN creation by, out of the box. It has that option. Others that do support are from Microsoft, right? So which created the DISKAN idea, right? So on their VectorDB instance, they do have this KN option, and they propagate or claim the same type of results that Metro and I and Solidigm did. Things to note. So when you're creating a DISKAN, important parameter is max degree. If you're working with HNSW, it's going to be M, but is how dense you want to be your index. So how many connections per point you want, right? Obviously, the higher the max degree or higher M, you have a larger index and a better quality index in that case, right? Search list. So when you are doing the search, so how big your candidate list. So once I do a query, how many, let's say, points, neighbors I fetch with that search, right? So you have those different parameters. So those are ones that you control upon creation and search. But internally to Milvus and any other DISKAN will have those type of settings, like the budget ratio, search cache, and the bin ratio. So also how it prunes data and how efficient it is, but they are not parameters that are open or that you can select. You have to go to Milvus config file and change those before you create the index. Yes?
Just out of curiosity, in your description for max degree and search list size, search list size is set to a value smaller than max degree, but your default is larger.
Yeah, and those are the defaults for Milvus.
Oh.
All right, so I took from Milvus documentation, those are what they mention when you open the documentation for Milvus. And I know but I had to be what the documentation said. Well, I might ask them. And again, just the footprint, how much each vector size would be. Obviously, we have drawbacks. One of the biggest drawback is how long does it take to build the index? DISKAN takes a long time to build the index, right? So that's a really big point of consideration, mainly not because you create just index once, right? You have to update this index constantly, and that will create this big problem to address because it takes awfully long time to create the index with current technologies, right? Just wanna mention that MLPerf storage is working on a vector DB benchmark. So if you want to join and help us, feel free. And my call to action, since I'm running out of time, is make real-time updates, right? So there's another DISKAN base called Fresh DISKAN that supports real-time updates. So this should be the direction we should take if implementing that. Address the indexing building time using GPU. In this, for NVIDIA, they have QVS, CUDA vector search, which has a Vemana graph index built. So technically, you could create a Vemana graph using GPU and then use the CPU for the search. Right? Still need to find out how, in my lab at least, how fast it is. But from GTC, they had good numbers, but they tested with only AJNSW, not with DISKANN on the last GTC. And extend support, like I mentioned, Milvus is the only one who supports DISKANN. Would be it is needed more support with other softwares, so we could more take advantage. And maybe from the storage community, we could provide this support. Yes, question? Mm-hmm. All right. Yeah, I have to look at it. I have, but those ideas to use different techniques, right? It's how you get the best result that you're looking for within your parameters. Like, and today we do have the, like you mentioned, quantized, but not straight here. So the way regular products are based, they're based on the regular 90% what people use. Well, thank you. That's kind of all of it. We kind of ran out of time, but we did some Q&A during the session, so that's fine. And feel free to approach and talk a little bit more. Thank you.